Hello guys, welcome to another video, and today we will try to prove one of the most famous theorems in mathematics, particularly in geometry, which is known as the Pythagorean theorem. So this theorem is famously known for its many uses in both pure mathematics and physics. So what this theorem basically says that if we have a right triangle and we denote its adjacent side as A, the length of its opposite side as B, and the hypotenuse as C, we will find that A squared plus B squared equals C squared. And specifically, this equation is the one that we will try to prove. Now, with that, let us now start our proof. So we need to show that A squared plus B squared is equal to C squared whenever A, B, and C are the adjacent side, the opposite side, and the hypotenuse, respectively. Right? So we just basically describe the variables that we have here, which are A, B, and C. Alright. So how should we start this? Well, let us consider the right triangle that we have above. Right? So we have this right triangle. So what we will do is we will try to duplicate this right triangle, then rotate it clockwise, okay, at exactly 90 degrees, and then place it on top like this. Okay, like so. And then we do it again, duplicate, then rotate clockwise, place it here, then duplicate, rotate it clockwise, and place it here until we get a quadrilateral, right? So I have here a ready-made image of that figure, okay? And as you can see, that's the exact thing that we did here, right? We just duplicate, rotate, duplicate, rotate, duplicate, rotate, okay? All right. Now, notice that the side length, all right, the side length of this quadrilateral is A plus B, correct? So this is A plus B, right? And notice we can also observe the same thing to the three other sides, right? So this is A plus B, this is A plus B, this is A plus B, okay? Now, since all of its sides are equal, then we can say it is either a square or a rhombus. But which is it? Is it a square or a rhombus? Alright, so the one thing that we also have to notice here is its angles. So notice all of its angles are all equal to 90 degrees exactly. Since this is the case, all of its angles and all of its sides are equal to each other, then hence this is a square, right? Now what is the area of this square? Or, as I would like to call, as the big square, right? Since it's big. Well, the area of this big square, we will denote it as a big, is equal to the square of a plus b. Okay, simply as that. Since all of its sides are equal to a plus b, then it is the square of a plus b. Okay, and also, we will also try to find the area of each of these right triangles. It seems that knowing the area of each of these triangles would be really useful later on, right? So what is the area of this right triangle? Well, the area of one right triangle, could be any of these four, is equal to AB over 2, right? Since our base here is A and our height is B, then you divide it by 2. Okay. Now notice that if we take the sum of all of these four right triangles and the area of this quadrilateral in the middle, we would get the area of the big square, right? So we already have the area of a right triangle, right? Which is AB over 2. But what is the area of this quadrilateral? Okay, so let's start figure out what kind of quadrilateral it is first. So notice that this quadrilateral is formed by this bunch of intersecting hypotenuse of each of these right triangles, right? So CC and so on and so forth. Now, as you can see, all of its sides are equal to each other, which are all equal to C. So, since this is the case, then we can say that this quadrilateral is either a rhombus or a square. But then again, which is it? Is it a square or a rhombus? Now to figure this out, we're gonna have to figure out the value of each of its angles, okay? So to do this, let's take a look at one right triangle, okay? So this is the right triangle. We will take a look at this. So we have the A, the B, and the C. Now what would I do is I would let the angle in this vertex to be alpha, okay? And this be beta. Now, we know that the sum of all interior angles of any triangle is equal to 180 degrees, right? So we find that alpha plus beta plus 90 degrees is equal to 180 degrees. So this would just mean that alpha plus beta is equal to 90 degrees exactly. Okay. Now, what we would do is this angle, we would let this be, let's say, theta or theta 1. Okay. Now, as you can see, that this is alpha, right? This is alpha and this is beta. And as you can see, when you take the sum of all of this angle, these three angles, it'll be exactly equal to 180 degrees, right? Since it forms a line. So we can see that alpha plus theta 1 plus beta is equal to 180 degrees. So doing some quick commutative property, this would mean that theta 1 plus alpha plus beta is equal to 180 degrees. But we know that alpha plus beta is equal to 90 degrees. So this means that theta 1 plus 90 degrees is equals to 180 degrees. So this would mean that theta 1 is equal to 90 degrees. That's good. So we know that theta 1 is equal to 90 degrees, right? But we still have 3 angles to go. So let's keep doing that. So again, let's try to denote this, say, theta 2. Right? Now, as you can see, this is the same scenario here, right? This basically means that if we have the angles alpha and then beta, right? That's just the same thing. We would find that theta 2 plus alpha plus beta is equal to 180 degrees, right? Now, since again, we found that alpha plus beta is equals to 90 degrees, then we can see that theta 2 plus 90 degrees is equals to 180 degrees. And then we can further deduce that theta 2 is 90 degrees. That's good. So this is 90, this is 90. How about this? Well, let's try to denote it as theta 3. Then again, this would be alpha, this would be beta. So I think you already see where's this going, right? So again, if this would mean that theta 3 plus alpha plus beta is equal to 180 degrees. Now, same exact thing, we can now then say that this is equal to 90 degrees, right? So, if we do it again, let's say we denote this as theta 4, okay, we denote this as theta 4, we could clearly see this would also just be theta 4 plus alpha plus beta being equal to 180 degrees. And we could clearly see that this is also equal to 90 degrees. Although from the beginning, we can just say that this figure has rotational symmetry with order 4, right? And just use that fact to conclude that each of these angles are exactly equal to 90 degrees. But I want to do it this way so that we can clearly see that each of these angles are equal to 90 degrees naturally. Now then, since all of its angles are equal to each other, in which all of them are exactly equal to 90 degrees, and all of its sides are equal, then hence, this quadrilateral here, inscribed within this big square, is a smaller square, right? So this is indeed a smaller square. So let's put that. So this is this small square. Okay, good. Now, what is the area of this small square? Well, it is just basically its side squared, right? So the area of the small squared, right, is equal to c squared. Just simple as that. And remember what I've said earlier, that if we take the sum of all of these 4 triangles and the area of this quadrilateral, which happens to be a small square, it'll exactly equal to the area of this whole figure, which we denoted earlier as the big square, right? So we can say that the area of the big square is equal to 4 times the area of the right triangles plus the area of the small square. And then we can say that the area of the big square is equal to 4 times the area of the right triangle is AB over 2. So this is AB over 2 plus the area of the small square is C squared, right? So this is C squared. And then let's simplify this even further, giving us that the area of the big square is equal to 2AB plus C squared. Now, we know that the area of the big square is basically the square of A plus B. So let us substitute that to our equation, giving us that the square of A plus B is equal to 2AB plus C squared. And then we can now then turn this into a perfect square trinomial, giving us A squared plus 2AB, yes, that's correct, plus B squared is equal to 2AB plus C squared. And then what we can do is just subtract 2AB from both sides. So this cancels, leaving us with A squared plus B squared equals C squared. And now we've finally deduced the equation that we want to show, which is A squared plus B squared is equal to C squared. And this proves the Pythagorean theorem, and this makes our proof done.